Hey Alex, how you doing? This one problem summarizes some really important ideas for 15.2 double integral problems. This is problem 16 from your book, and the instructions are take this integral and write it both ways with dy dx here or dx dy. You got to do them both. Here's the domain that they give you right here. So it's bounded by y equals 4, x equals 0, and the slanted line y equals x. So this is the origin right here. So that's our region. If you go to do this problem with dy dx, okay, that means it's the little vertical boxes. So the top curve has to be y equals, and this top curve is y equals 4. The bottom curve has to be y equals, because it's dy, y equals x. Now, x's have to be numbers. What actual x numbers happen here? Well, it's y equals 4 on the line y equals x, so this is the 0.44. So x goes from 0 to 4. And now this integral is ready to go. Now let's do the other side, because they said do both. Now watch over here. Now this is x equals, and this is the top curve. This guy's the top, because it has the higher x coordinates. For this box, the higher x coordinates are here. So this is x equals y. And the bottom curve is x equals 0. And now what does y do? Y goes from here to here. That's 0 to 4. And now we go to the scientific workplace computer algebra system and see what they make of these two integrals, because the instructions make it sound as if one of these integrals is better to do than the other one. Now, one of these is easier. Well, let's see. Let's see what computer says. So if I did this right, I've typed in the limits of integration that we just found. And I'm going to ask the computer algebra system, hey, do this one. Evaluate. And that's the book answer. That's an actual number. You can get that integral because this first part right here, this integral becomes, stick a y out here, you have y e to the xy dx. That's doable by chain rule. It's a regular chain rule integral. When we do this thing, you have the derivative of the upstairs with respect to x is y. This is just going to be this y out front, e to the xy, evaluated from 0 to y. And then you do the other integral around it. But it's doable. Now let's ask the scientific workplace for this integral. This guy, if you take a second, how would you integrate this? You get the integral of y squared, e to the, let's make that x a 5. How would you do that integral? That's a Calc 2 integral. That's a tabular integration by parts. That is not an easy integral. It's not easy. It's doable, but I wouldn't want to do it. So what the book is doing here is illustrating for you that, by the way, the dy dx or dx dy matters sometimes. And choose the easier way. Your life is better. You get the problem done faster. Let's see what the computer algebra system makes of this. Hey, evaluate. And all it does is spit the integral back out, because even the computer algebra system doesn't know what to do. We could do it by hand. It would take a long time. But the computer's stuck. Whatever algorithms it has, none of those apply to this problem. It doesn't know what to do. Isn't that funny? But let's give it a shot at numerical. Evaluate numerically. And I get an answer 4 million something. Well, let's evaluate this e to the 16 thing, because that looks like it could be kind of beefy as well. Evaluate numerically, and it's the same answer. So yeah, this guy doesn't know how to do the theoretical, but can estimate it. And the estimate matches the value of this number. We could do this one by hand, but what would be the point? It's much easier this way. This one you can do by hand. And that's what we did today. See you later.